So this is the outline for my presentation. I will first do a very quick recap of the work done in previous weeks. Next, I will give an update of my team's latest progress, namely an investigation into X-Plane's modeling of the water mechanics, an overview of the aircraft components I am responsible for modeling, and finally, the updated version of our SFV model, the CPIC Mark II. And lastly, I will go over our team's outlook for next week. So first, a short recap. In the first week, we concentrated on doing our literature review. We went over the US Naval Flight Test Manual and familiarized ourselves with the X-Plane, PlaneMaker, and AirForeMaker software. At the end of the week, we had come up with a detailed list of flight testing procedures. Our second week was spent practicing with PlaneMaker and AirForeMaker software. The product of our efforts was the original CPIC model, which we showcased during last week's presentation. And now an update on our latest progress. Firstly, our team explored X-Plane's modeling of water mechanics. So X-Plane provides a C-plane model by default, namely it's the Bombardier 415. And it also provides special options to perform seaplane takeoff and landing maneuvers. So based on this, we have reason to believe that X-Plane has been designed such that it is capable of modeling flight mechanics on the water surface with reasonable accuracy. To verify this further, we attempted a water takeoff with the Bombardier 415. And using X-Plane's inbuilt data recording system, we recorded a takeoff distance of 2,900 feet. Against the advertised aircraft's takeoff distance of 2,670 feet, this amounts to about a 10% deviation. And factoring in deviation caused by pilot error and inexperience, namely us being the pilots, the result is rather encouraging and suggests that the water surface mechanics are modeled with decent accuracy. Next, we explored the depth of ground effect representation. And we found that X-Plane does indeed model ground effect. However, instead of changing the flow over the aircraft surfaces, what X-Plane does is that it uses empirical approximations to alter the lift and drag values on the aircraft. And the empirical multipliers employed are determined by wing characteristics such as aspect ratio, taper ratio, dihedral, and the employment of any high lift devices. So, however, on the whole, our online research our online research on the accuracy of ground effect representation did not yield two concrete results. The majority of what we found constituted subjective pilot opinions, comparisons of what they experienced in the actual aircraft versus what they experienced in the simulator. And on the whole, even though most of the opinions said that the ground effect modeling was realistic, we wished to make further verifications ourselves. So we recorded the ground effect data while flying the latest iteration of our aircraft at different altitudes above the water surface. So the numbers are a bit small, I'm sorry. I'll verbally explain what the pictures are saying. So this picture is taken flying 10 feet above the water surface. And there's actually no effect on the lift coefficient, but there is a 30% reduction in induced drag. This is flying 5 feet above the water. There's a 7% increase in lift coefficient and a 35% decrease in induced drag. And finally, this is 2 feet above the water surface, which is dangerously close to the water surface, but you see that there is a 10% increase in lift and a 40% decrease in induced drag. So all these simulation situations show quite clearly that X-Plane does make an attempt to model ground effect, and it's also essentially consistent with our expectations, which is that ground effect should reduce the induced drag further the closer you get to the surface. So last week, Kai went over the modeling of the wings and tailplane, so that everyone has a better idea of how their design inputs will be incorporated into the X-Plane model. Today I will go through the aircraft components that I am responsible for. So first of all, the fuselage. While CAD software primarily uses graphical sketching inputs to model the fuselage, PlaneMaker primarily requires numerical inputs instead. So essentially what is needed for the fuselage to be formed is a set of 20 planar cross-sections, a maximum of 20, you could use less if you wanted, but no more. And for half of each cross-section, the coordinates of 9 discrete points have to be defined. And PlaneMaker assumes that your fuselage is going to be symmetrical. So after defining these 9 points on half the cross-section, the points are mirrored along the vertical axis, and then you have the complete cross-section. And after that, with all the cross-sections defined, PlaneMaker automatically assembles all the different cross-sections together. So for maximum accuracy in modeling, the coordinates of the discrete points are extracted from the CAD model. So the extraction of points from the model, the CAD model is shown on the left. The first step is to extrude or cut the fuselage section to expose the desired cross-section. And then 9 datum points are then marked out by locating the intersection points between the cross-section surface and equally spaced axis lines. The x, y, and z distance of these points with respect to the reference being the nose of the fuselage, are measured and then tabulated. And on the right, you can see the entering of the fuselage coordinates into PlaneMaker. So each column on the right corresponds to a single half cross-section. In the top box, the user is able to define how far away the cross-section is from the nose. And in the lower two boxes, the user is able to accurately define the coordinates of the 9 discrete points. So the entire process is rather lengthy, but it's not difficult. And the modeling of the engine is relatively straightforward. PlaneMaker allows you to enter the engine's key specifications, such as the type, the number of engines you have, any transmission losses, fuel consumption values, and so on. The size and shape of the engine nacelles are modeled similarly to the fuselage, in that you have to define cross-sections and discrete points along the cross-sections. The only difference being that instead of 20 cross-sections as per the fuselage, you are now able to only define 12 cross-sections. And finally, the pylons are actually modeled geometrically as very thin wings. Not that they produce lift, but they're very close in appearance to wings, so the interface is similar to that for creating wings. So here's a snapshot of the engine creation interface in PlaneMaker. I won't go through all the options because there are a bit too many, but this is just to provide a glimpse into the level of detail you're able to program into PlaneMaker for the engines. So the modeling of the undercarriage is also quite straightforward. The user has to define the undercarriage configuration, whether it's a bicycle, tricycle, nose dragger, tail dragger, and so on. And the individual strut specifications also have to be defined. And finally, the gear doors are modeled separately, and then they are merged together with the landing gears. So on the right is a list of all the specifications for the landing gear that the user can define. Among other things, you can define the strut position, the length of the struts, the tire dimensions, and retraction angles. And on the left is a creation tab for the gear doors. And the door creation is actually quite simple. You simply have to define the door shape, the location, and the movement angles. Finally, a significant amount of our time this week was spent updating our aircraft model. With reference to the provided CAD model, and taking into account design inputs from our group members, we made changes to the original CPIX fuselage, engines, aerofoils, wings, and tailplane. And thus we have the CPIX Mark II, as we call it. So here's a comparison of our latest version with the original. The fuselage now incorporates the proper hull shape. The engines have been changed from rockets, for fun last week, to turboprops. And at the time of updating the model, we did not have the complete information about the turboprop yet, so the horsepower, dimensions, and fuel consumption values were taken from the propulsion team, and the rest of the engine specifications were taken from the Bombardier 415. Kai also updated the aerofoils according to inputs from the aerodynamics team, and the wings also now incorporate winglets and pontoons for water stability. So with the added hull-shaped fuselage and wingtip pontoons, we decided to try a water takeoff with the CPIX Mark II. So I'm just opening manually. Yep, this is the result. Okay, so even though the plane is able to take off in the water and it looks pretty nice, the aircraft was not modeled entirely with design inputs from the rest of our team, so it's quite difficult for us to make any conclusive statements or to give any useful feedback at this stage. So to round off, this is our team's outlook for next week. According to our original project timeline, our team is still quite on schedule. For the following week, we hope to be able to test a fully designed aircraft model and provide comprehensive feedback for our team members. And that concludes my presentation for today. Thank you.
The results that you quoted for ground effect are actually quite interesting. What was the process for doing those flight tests? What did you keep constant? What did you vary?
I basically try to keep the indicator airspeed constant. It was around 250 knots from what I recall. It's not shown in this diagram here. And I tried to keep the aircraft at a stable altitude above the water level, which was quite difficult actually because the control surfaces were just the default recommended values from X-Plane. So it's quite difficult to control the aircraft in that sense. But yeah, so after maintaining the aircraft at the altitude for about at least 5 seconds, then I took a snapshot of the data output, which is a built-in function in X-Plane. So it gives you the changes in lift coefficient for the wings and all the stabilizers, as well as the changes in the induced drag coefficient as a factor of 1.
So
yeah.
These values that you got, were you able to compare them to anything? So you said they sounded right, but things often sound right but are not.
Well, what I meant when I said that it sounded right is more of the trend seems correct, and that the closer you get to the surface, you get even more reduction in induced drag. But as for comparison with actual results, I think it would actually be more useful if we could compare it at the design speed for our aircraft, as well as the design altitude rebound effect. From my correspondence with the aerodynamics team, I believe we'll be flying, well, as of now, we'll be flying around 60 feet above the water level, although that is also subject to change. So once that has been finalized, Kai and I will conduct a proper flight test at the design altitude and also at the design speed. Yeah. And then we can make better comparisons then.
So how much, this is sort of the same question again, sorry, how much of a saving do you expect? Or what's your recommendation to the aerodynamics team for the flight test?
Well,
have they told you we think at 16 feet we're going to save X% drag?
Yeah, I tried to ask the aerodynamics team about their progress, but from what I understand, they have been focusing on other areas for now. So for ground effect, their results have been quite preliminary, and I only understand that once the airplane is about wingspan level above the water surface, they expect to start seeing changes in lift and induced drag. But as for exact values as to how many percentage increase or decrease in lift and induced drag, no, I don't have any yet right now, unfortunately.
You said that you compared the CL415 takeoff distance. Was this the takeoff run, or was this takeoff to 50 feet or 35 feet?
50 feet.
Okay.
50 feet, according to DEFSTAN regulations. Well, apparently DEFSTAN does not have explicit regulations for seaplane takeoff, but for takeoff from land, it specifies that you have to clear an obstacle of 50 feet. So we decided to just use the same thing for the water takeoff.
Okay.
Yeah.
And the value that you're using is also for an obstacle of 50 feet then?
Yes, I believe so.
Okay. And going from this, do you know how X-Plane models water at all? You said it's a pretty good model, but do you have any idea of how it goes about it?
Well, as for the specifics of how it models the water, unfortunately we need to do further research into that in order to give you more detail. But as a preliminary gauge of how accurate we can expect our results to be, I think we can say, well, right now at least, until we know further, we can say that the modeling will be reasonably accurate.
Right.
Thank you.